We are doing complex analysis. I hope that's not misspelled. I feel like it might be. So, what is this about? This is calculus for functions from the complex numbers to the complex numbers. This is what this subject is. And it turns out that calculus from the complex numbers to the complex numbers has a dramatically different feel than calculus from the real numbers to the real numbers. It is a strange kind of subject in its own right. It's one of two areas that you'll encounter in elementary mathematics, or perhaps all of mathematics, where almost any question you can ask, you can actually answer. So the other area is linear algebra. And many of the technical difficulties and complications from doing calculus, higher dimensional calculus, multivariable calculus, and then the outgrowth of these, all these things vanish, all these technical difficulties vanish in this subject. So when you come down to the kind of more fundamental issues, topological issues underlying the questions you want to ask and answer, it also is very intimately connected with various other areas of mathematics. In particular, it's very connected to PDE. And indeed, a lot of these theorems are special cases of more general theorems in PDE. It's a very remarkable and strange area. And it must have been incredibly exciting in the 17th century when it was discovered because it just opened up some strange new world. It's the first example of doing mathematics in a space which is not our natural space of the real numbers or three-dimensional space, where you prove theorems in this new world and you learn things about the world you live in, which is the world of the real numbers, the world of three-dimensional space, the world of real integrals. So that must have been so shocking to people back then that you could enter this world, prove these theorems in this world, and then it tells you stuff about your world, the world you live in. So that's one of the reasons it's very popular to teach at graduate level. It's a way to prove, it's an area you can prove very deep theorems without much discussion of complicated technicalities. You can get rather quickly to the heart of the issue. Many of these very deep theorems are actually quite easy to prove. Hopefully I can give you some sort of flavor of this as we go along. But first we have to do the preliminaries. We have to talk about the basic stuff, the field of complex numbers. We have to set this whole game up. Once we understand this basic stuff of the complex numbers themselves, we're going to start to discuss functions, and then the real subject gets going. So let's do the very basic thing. So what are complex numbers? These are numbers, x plus iy, this way, where, as you know, I is square root of -1, which is something we just have to accept, that there is this thing, the square root of -1. It doesn't exist in the real world, but let's just define I to be this thing, and let's just go forward with it. That's what complex numbers are. Okay, so we have a real part, which is the x, and then I times y, which is the imaginary part. Now we're going to write z, which is like this. And what is cool about this collection of numbers is that it actually forms a field, that we have these two operations that act in a very natural way. So addition is kind of straightforward, that if we have z1, which is x1 plus i1, z2, which then we can just add them. So we have z1 plus z2 Yep, that's pretty easy, right? That's kind of natural. We also have a multiplication. So if we multiply these numbers, let me turn up the light on the board a little bit. If we multiply these numbers, we have x1. Then we just multiply through all this stuff and see what we get. So if we multiply the x1 through all this, we have x1, x2 plus I, x1, y2. And then we multiply the I, y1 through the rest of this stuff. We have I, y1, x2. And then using the fact that I squared is minus 1, we have minus y1, y2. And then this thing is what? Is x1, x2 minus y1. y2 plus I of y1 x2 plus y2 x1, like this. And this is our multiplication operator. This multiplies two complex numbers, gives us a complex number out. Yeah? Cool. So, what are the good things about this? Well, this is commutative. So both operations are commutative. And that's you can just check this, just do this, the Z2 in front of the Z1 comes out exactly the same way, and this is kind of obvious that it's commutative. So we have Z2, Z1, Z1, Z2, and okay. And all of you people at this point now know that there are natural mathematical objects that are not commutative. Can you give me an example of one? Give me an example of a class of mathematical
matrices and matrices.
Yeah. So matrices, for example, are not commutative. If we compose them, then the order at which we do it definitely matters, right? So this is something you don't have for free for every mathematical object you create, but it is true in this case. And it has the other nice algebraic properties we want. It's associative, it's distributive. It behaves algebraically just as nicely as the natural numbers, as the real numbers. And everything we want to do algebraically in terms of this kind of stuff, multiplying through a bracket, all that stuff goes perfectly well. All that stuff is perfectly good. Okay, so this is a nice collection of numbers from the perspective of algebraic operations. Everything is happening the way we want. But this is a two-dimensional set of numbers. Let me say this better. This set of numbers forms a two-dimensional object, right? Because it is defined by an x and a y. So the real numbers is obviously a one-dimensional thing. This is a two-dimensional thing. So we have this two-dimensional set that actually forms a field. Yeah? It forms a field. A really nice, convenient kind of algebraically convenient way. And being two-dimensional, we like to think of this like to represent it. And we represent it as points in the plane, typically. So we're going to think of this axis as being the real numbers, and this axis as being the imaginary numbers. So let me actually write that like I times R. And then everything can be considered as a point in this complex plane. Yeah, just like when we consider vectors x, y. So this is how far we are along on the x, and this is how far we are along on the y up here. Yeah, cool. So let me get rid of this because it looks ugly. So this is how we think about complex numbers. And if we think about complex numbers this way, then the additive laws just behave exactly as you would expect. So if we have some complex number x1 plus I y1, and then some other complex number x2 plus I y2, and we add them together, that's the same as taking this complex number and sticking it onto the end of this guy like this. Oops, I guess that's too long. Okay, and this thing here, see if I can change color again. I guess not. This thing here, which goes from here to here, is this vector x1 plus x2 plus I of y1 plus y2, like this. Okay? Just as you learn when you were learning multivariable calculus and you were learning to add vectors, exactly the same thing happens. Oh? Cool. So we can visually represent adding these complex numbers in a natural way. Yeah? Good. So, basic algebraic laws or inequalities also hold. So we have, from this, we can see we have the triangle inequality, that if we take Z1, Z2 belonging to the complex numbers, then if we take the absolute value, I should tell you what the absolute value is first. Okay, let me pause for a second and tell you what the absolute value is. So the absolute value I'm going to abbreviate to ABS of a complex number mod Z is the square root of x squared plus y squared, where Z equals x plus iy. Yeah? That is the absolute value of this complex number, and visually we can understand this as just being the length of this line right here, which goes from 0 to x plus iy. Yeah? This is the absolute value of x plus iy. Yeah? So, if we have two vectors, Z1, sorry, if we have two complex numbers, Z1 and Z2, and we take the absolute value of the sum of them, yeah, turns out that this is less than this thing, yeah, which, again, we can just see from this picture. So what I'm going to do, I'm trying to perspective I'm going to sell to you, is to visualize mathematics analysis all the time. This is one of the key things that I'm going to try and get you into, to try and, well, so this might be my philosophical perspective on maths. Well, I hope not. I hope it's everybody's philosophical perspective. But maths, for me, is a language that describes pictures that you can, in many cases, literally draw on a piece of paper. But in other cases, things you can't really draw, but nevertheless, in your brain, they feel like pictures. If you understand them well, it is something like having a picture in your head. And for as much as possible, I'm going to go from this language to the pictures to explain things. That's how I understand things. That's one of my main tools in research, is to visualize things. When I say visualize, it doesn't literally mean have pictures, but have something that is something like a picture. As you are entering research, you're going to have to understand maths perhaps in a deeper way than you've understood before. That's something I want you to learn as quickly as possible, to take this stuff out from the language, these symbols on a board or a piece of paper, and put it into pictures in your head. And once you have the pictures in your head, then all of this stuff, all of these details are kind of minor and unimportant. You can easily recapture them. So I'm going to be drawing pictures all the time, and I want you to think in terms of pictures all the time. If you see something I've written down, some theorem, some remark, whatever, and you don't have a picture, you can't draw a picture, or you don't feel a picture in your head, then you haven't understood it. I don't want you to understand things in terms of manipulations we do on symbols. That's kind of the last stage. Once you have a clear idea, then you have this language that you can express your ideas in. But that's not the real thing. The real thing is having the clear idea, having the reason, having the picture, and the actual proof, the actual description in the language is not the actual math. That is just the way we represent it, in the same way that music is represented by a musical score. The musical score is not the music. It is just the way to represent it. So try and get into this perspective as quickly as possible. Do not be happy with things that you can prove by knowing a sequence of symbols that you can write down. Only be happy with things that you can prove or explain because you have a picture, and you don't, and whatever the symbols are, you could choose a whole bunch of different notation, whatever, it doesn't matter. The picture is the real thing, okay? So whenever I do something and it doesn't seem clear, I'm going to try and draw pictures, and feel free to ask me what the picture of anything is at any point, because I should be able to explain practically everything in terms of pictures. All right, good. So back to this. We have this rule, and we understand it in terms of this picture. We have that this quantity absolute value of Z1 is this length. This quantity absolute value of Z2 is this length, right? And then we can see from the picture that this length plus this length is equal to is greater than this length. Yeah. So the triangle inequality is just rather easy from pictures, and we have, as a consequence of this kind of inequality, if you Z1 minus Z2, this is less than equal to Z1 minus Z2, which we just get from doing the triangle inequality and applying it to like this. So Z1 minus Z2 plus Z2 by the triangle inequality is less than Z1 minus Z2 plus mod of Z2. And then this thing here is just Z1 itself. So we have that Z1 minus Z2 absolute value is less than Z1 minus Z2, like this. And then we can reverse the order and then get also that Z2 minus Z1 is less than Z1 minus Z2, which gives us this thing which we will use later on. Okay, cool. So these are the basic properties of complex numbers that we need so far. Okay, so more algebraic stuff. So complex conjugate. Don't know how to spell. Oh God, I guess it's with a J. So something I have to confess is that I don't know how to spell even very simple words. So conjugate. Maybe it's something like this. Complex conjugate. All right, so this is an operation we do on the complex numbers where we do the following. So if we have Z, which is X plus IY, then the complex conjugate Z bar is X minus IY. And of course, it comes with a picture. So if this is our Z, which is X plus IY, then the complex conjugate is the mirror image over here. And this is just an algebraic operation we're doing on complex numbers. It has a number of convenience properties that we will use lots of times. So this is nothing deep. It's just this thing that is notationally convenient to write that we're going to go from the complex number to the mirror image across the real axis via this operation. And here's some of the nice properties. So this is easy to see. If we have Z1 and Z2 belonging to the complex numbers, then just Z1 plus Z2. When you do the complex conjugate, just from this definition, it's kind of immediate that this is true. Okay. Another thing which is true, and it's kind of another algebraic thing, which is pretty straightforward, is if we take these two complex numbers and multiply them together, that's the same as the complex conjugate of each one multiplied. Okay, so complex conjugate behaves nicely with respect to this operation. That stuff is cool. All right, another cool thing. If we take z and we multiply with this complex conjugate. So we're going to take z to be x plus iy. Let's see what happened. We have x plus iy, x minus iy. When we multiply this stuff through, the i's will just cancel out each other because we're going to have an iy times x and a minus iy times x. So we're just going to have the x squared, and then this thing will be minus I squared y squared, which would just be y squared itself, which is just the absolute value of z squared. Okay, so we can quickly come up with the absolute value of a complex number by multiplying it by its complex conjugate. That's another useful algebraic fact we will use. Here's some definition. We say that the real part of this complex number z, which again is x plus iy, this thing is just the x. And the imaginary part of z, this thing is just the y. Okay? And another easy algebraic fact is that if we add together z and its complex conjugate, if we add this to this, we see that the iy thing will cancel, right? We have iy plus minus iy, right? So if we add this together, we're just going to get 2x. Yeah? So if we just divide by 2, we get x, which is the real part of the complex number. Yeah? And then we can do something similar to find the imaginary part. If we take z and then we minus z complex conjugate, so look at this. If we take z minus this thing, then the x's will cancel. So we'll have iy minus minus iy, which will be 2iy. Yeah? So if we divide this stuff by 2i, we're just going to get y, which is the imaginary part of z. Yeah? Cool. All right, so these are useful things. Now, let's go on to the polar representation of complex numbers. So, if we have some number z, which is equal to x plus iy, recall we can think of this as a point in the plane, the complex plane, x plus iy. Polar representation of complex numbers is that we are going to represent this thing, which consists of two numbers, with a radius and an angle. And the radius is the length of the line joining 0, 0 to this complex number, and the angle is the angle from the positive real numbers. Okay? Yeah? So you learned this hopefully already, that for every xy, we can represent it with an r theta like this. Yeah? And what we are going to do here is a kind of equivalent thing. I'm going to start with defining this thing. So define e to the I theta by cosine of theta plus I sine of theta. We can define this, right? This is a well-defined thing. What is this? Well, this is effectively a map from theta to the unit circle in the complex numbers, right? So theta goes to, let me write it like this. We have the real numbers goes into the complex numbers via theta goes to e to the I theta. And what does it do? It sends theta to all things that are unit distance away from the origin. Yeah? Because as we run around theta, all of these things are complex numbers of length 1. Yeah? Everybody clear? Cool. So this is e to the I theta, okay? And the polar representation is where we write z is equal to r e to the I theta, where r is the absolute value of z, and theta is the angle that produces this thing, which is defined up to 2 pi k, where k is any integer. Right? This number, as I've written it, is not uniquely defined, because for whatever angle I have whatever pi pi plus this angle, 4 pi, whatever angle I have 2 pi plus this angle, 4 pi plus this angle, 6 pi minus 8 pi, whatever. It's always going to define the same angle. Yeah? Because when we put in that into this, it's not going to change anything. If I put in if I put in theta or theta plus 8 pi, this produces exactly the same thing. Yeah? So this thing here, this angle, is not defined uniquely. It's defined modulo 2 pi times the integers. Yeah? So we write this. So z is 2 pi like this, which is when you quotient out the 2 pi z. So i.e. we consider theta 1 and theta 2 inside this thing, 2 pi z, equal to each other. And this is a sentence: if this and in this group, this is equivalent to saying that theta 1 minus theta 2 is 2 pi times k for some k inside the integers. Yeah? So in this sense, it's uniquely defined, but if we just consider it on the real line, it's not uniquely defined. Yeah? And this will be actually a kind of issue we come up with. This will be important going forward. Okay, so what is cool about the polar representation of complex numbers? Okay, so what is cool about this polar representation is that it allows us to understand multiplication in a geometric way. So if we have z1, and let's write it in its polar form. So we're going to have r1 e to the I theta 1, okay? And we have z2, which is r2 e to the I theta 2, yeah? Then let's see what happens when we multiply it. So if we multiply z1 and z2, then that's going to be the same as r1 times r2 of e to the I theta 1 e to the I theta 2, yeah? Because it's commutative, I can just pull out the r1 and r2 because they themselves are just complex numbers. So I can write it this way. Everybody cool? Yeah? And then what? Then this thing is r1, r2. Let's write it out. Cosine of theta 1 plus I theta 2. Cosine of theta 2 plus I sine of theta 2. And then when we multiply that stuff out, we have r1, r2, and we're going to have cosine of theta 1, cosine of theta 2 from here to here, and then minus sine of, this should be 1 here, theta 1, sine of theta 2, just multiplying out this thing times this thing and this thing times this thing, and then r1, r2, and then the imaginary part, which is this thing times this thing and this thing times this thing. So let's actually just put the I out here, and we're going to have sine of theta 1, cosine of theta 2, and then this thing, so we have this thing times this thing, and then this thing times this thing. So we have cosine of theta 1, sine of theta 2. Yeah, and we all recall our trig identity. So recall, having a pen here, so recall that if we have cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2, this is nothing other than cosine of theta 1 plus theta 2. It's one of our standard trig identities. Huh? Identities. And we also have the following thing, that sine of theta 1 cosine of theta 2 plus cosine of theta 1 sine of theta 2. This is sine of theta 1 plus theta 2, another basic trig identity. Okay, so with these two facts, putting them directly into this, let's change it back to the color. So Z1 times Z2 is equal to R1, R2 of cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2, like this. Yeah. And then that thing is just equal to R1, R2, using this e to the I notation of theta 1 plus theta 2. Yeah? That's what we see just from the fact we have these trig identities and the multiplication laws for complex numbers. Yeah? Cool. So let's see what that means geometrically. That means that if we have these complex numbers, this one, Z1, so this here is the angle theta 1, and another one, let's say this guy here is Z2, and this is the angle theta 2, then what happens? Well, when we multiply them together, the thing that we get has got angle theta 1 plus theta 2 away from the positive real numbers, right? So the multiplication of these two produces this thing, which is kind of like this. This thing is got the angle theta 1 plus theta 2. Yeah? And what happens to the actual modulus? The modulus is the multiplication of the modulus of these two complex numbers. So when I say modulus, I mean absolute value. I'm going to use these words interchangeably. Okay? So the absolute value of our new complex number is the product of the lengths of the previous ones. Right? So this thing here is Z1 times Z2. Cool. So now that gives us a way to understand geometrically both of the field operations of the complex numbers. When we add the complex numbers, we are just adding the vectors in the way that we've learned to add vectors. That thing is quite standard. Now, this multiplication operation, we understand what that thing is doing. It's taking our two complex numbers with our angles, yeah? And when we multiply them, the new complex number is the sum of these two angles times the multiple of the length of the absolute value, times the product of the length of the absolute values. Yeah? Which is a very neat geometrical thing to understand. This is a very clear thing. So previously this algebraic operation of multiplying, which was consistent with the fact that we have defined -1, or we defined I to be square root of -1, this now has meaning in terms of seeing what these complex numbers do to each other when we multiply them together. Yeah? Cool. And that's going to be very useful for us going forward, as we'll see. Another thing to note is that if you don't remember your trig identities, which I certainly don't, you can always recover them from this fact right here, right? So if you remember the fact that when you multiply, so just note, if you remember your complex analysis, that when you multiply this complex number with this complex number, it's equal to this complex number. We use the trig identities to get this fact, but if you assume this fact, you can get back the trig identities, right? Because if you write out what this means that this thing here, which is this thing here, this thing, which is this thing, is equal to this thing, which is this thing plus I times this thing. Huh? So from this, you can recover these two trig identities. Yeah? So you don't have to struggle with remembering these things. This is quite an easy thing to remember. And this thing implies both of these things just by writing out the real and imaginary parts of this complex number and this complex number. Yeah? So, and actually, okay, let me not go into a tangent. So this thing is a cool thing to have in mind when you want to recover trig identities. Cool. All right, so let's maybe talk about the field a bit more. So since we now know the field, we know how to add these numbers, we know how to multiply them, we have some idea what it means. We're going to talk about some metric properties in a second, but let me just talk a bit more generally about the field. So in England, for historical reasons, we learn complex analysis in the second year of undergraduate, and it's supposed, at least if you're doing a degree in maths, at least that was the way it worked in my day. And it's quite an advanced subject, as you know, this is a graduate course here in America. So most students don't understand it very well, and I was certainly one of them. And one of the things I found off-putting about this subject, and this might sound ridiculous, was that I didn't like that we had to deal with I, which was the square root of -1. So like the 15th century mathematicians, whatever, to me this seemed a bit odd. The whole thing just seemed odd for exactly this reason, that we're working in this set of numbers which weren't real, that didn't have a meaning in the real world. So I was a little bit kind of skeptical of the whole subject to begin with, and kind of speaks to my lack of mathematical maturity, age 19. But nevertheless, if you are like me, well, I have to confess, this was in my mind for actually a long time afterwards, that all of this stuff is about something that doesn't exist. Square root of -1 doesn't exist. So it was sometime later that it was pointed out to me, I saw somewhere, that we don't actually have to deal with square root of -1. We don't have to deal with complex numbers at all to do complex analysis, because of the following thing, that if we just step back for a second, what we're dealing with here is a field of numbers, two-dimensional field, where we can add them and multiply them in nice ways. And here's another field that we can add and multiply in nice ways. In fact, I'm going to show you it's exactly the same. It's going to do exactly the same thing as complex numbers. So I'm going to define the conformal matrices, which is something we're going to need later on anyway. So conformal matrices, this set. So it's a set of 2 by 2 matrices of this form: A minus B, B, A, where A and B are real numbers. Okay, that's the conformal matrices. So this is the same as the set of all lambda times a rotation matrix, which I'll write as R of theta. So where theta is any real number, and R of theta is cosine of theta minus sine of theta, sine of theta, cosine of theta. Okay? So this thing I claim is a field, and it has all the properties that we want. So we can certainly add numbers, right? Or we can add elements of this field. So if we have, say, A and B belonging to these conformal matrices, I call it A and B. Let's call it A1 and A2. So A1 and A2. Then A1 is, say, A1 minus B1, B1, A1, A2, A2 minus B2, B2, A2, and we know how to add matrices. So A1 plus A2 is A1 plus A2 minus B1 plus B2, B1 plus B2, A1 plus A2, which itself is a conformal matrix, right? So we can add conformal matrices. We're back in the space of conformal matrices, That's not a surprise. Probably not also a surprise that if we multiply these two guys, something similar happens. Then we have A1 minus B1, B1, A1, A2 minus B2, B2, A2, and we know how to multiply matrices. That's well defined, right? So what we get, this column times this column, we're going to have A1, A2 plus or minus B1, B2. We're taking this column, acting on this row to get the first entry. We know how to do this, right? Then we're going to have A2, B1 plus A1, B2, this column acting on this row, then this guy, this column acting on this row, we are going to have minus B2, A1, minus B1, A2, and then finally this thing acting on this thing, we are going to have minus B1, B2 plus A1, A2, And sure enough, this is a conformal matrix again. This is the same as this, and this guy is minus this guy, So with multiplication, these conformal matrices are all good. We multiply them together, we're back in the conformal matrices. What is also cool about this is that this is commutative. So multiplying matrices normally is not commutative. This thing is commutative, okay? And you can kind of see that because what we're actually doing is multiplying rotations times a dilation, because these things are just rotations times a dilation. And you should know that if you multiply rotations, you can do that in any order, right? So if you have two rotations, you rotate the first one, then the second one, that's the same as rotating the second one and the first one. So this is actually commutative. It's an algebraic fact, but from the fact that we know this is basically, or this is exactly a dilation times a rotation, it shouldn't be a surprise that this thing is the same as this thing. So we actually have a commutative operation of multiplication on this two-dimensional field. Cool. And what else? Well, let's just write this. Let's write A, B, with a bracket and a little c, let's take that notation to mean this. Okay? Then, what do we know? Then we have that A1, B1 is A1 plus A2, B1 plus B2. See, that's the first thing we just did over there. And then this thing tells us that if we multiply these things, A1, A2, A1, B1, A2, B2, then this thing is A1, A2 minus B1, B2, A1, or A2, B1, plus, that should be A1 right here, A1, B2. Okay? That's what this second line tells us just here. And in fact, what is this telling us? This is telling us that the operations of addition and multiplication are doing exactly the same thing as the complex numbers. Because when we multiply complex numbers, A1 plus IB1, A2 plus IB2, we get exactly this stuff right here. Yeah? Yeah? You see what I mean? So what we actually have is a field that behaves in exactly the same way as the complex numbers. If we make this identification of A plus IB is like the conformal matrix defined by this AB, then every single step of every proof we will do will be exactly the same, because these operations are exactly the same. They're doing exactly the same thing. So if we, instead of doing calculus from the complex plane to the complex plane, we decide to do calculus from the conformal matrices, which is a nice two-dimensional linear space. So we consider the space of functions from the conformal matrices to the conformal matrices, and we try and develop the calculus of that, what we will have is a completely identical theory to the theory of complex numbers. Yeah? And in fact, morally speaking, these things are exactly the same. These things are exactly the same. So we're not developing an identical theory, we're developing the same theory. Because all we care about, all we're doing is we have a two-dimensional field that has these nice algebraic operations of addition and multiplication. And those operations are identical for the complex numbers and for the conformal matrices. Okay? So if, like me, age 19 and quite a number of years later, you were kind of skeptical about this subject because you didn't like I, you didn't like square root of -1, there's no need to actually have square root of -1 in this course. I could just never mention it. I could not mention it in the beginning and never mention it ever, because it's not needed here. It's not needed here. No? All that is needed is we have a field with these nice operations that behave in this way, and then we develop the entire theory this way. Yeah? So for me, conformal matrices, rotations times a dilation, are actually a more natural thing. You can see them in the real world than complex numbers, but actually they're exactly the same thing. They're exactly the same thing. Okay? But for traditional reasons, we're not going to do that. We're actually going to do things with complex numbers, but just keep in mind that it is nothing more than a kind of notational convenience to have something like this. The real important thing is these algebraic operations that follow from defining I to be the square root of -1, so that in particular when we multiply I by itself, we get -1. Yeah? That's the property that defines this multiplication operation. Yeah? But it's not an essential feature of what we're about to do. Yeah? So think of this as just a very convenient notation, and it is an extremely convenient notation to deal with this. So in my own work, I'm often using this notation even when doing things in the which are not to do with complex analysis, that are real analysis, because this notation is incredibly convenient in lots of ways. So this is more notation than an actual real thing. All right, so that is our field. Now let's talk about some properties of convergence after I clean this board. Okay, so we have this notion of absolute value, the length of a complex number, which gives us a metric on complex numbers. So we're going to have this thing is the distance between two complex numbers. It's the metric on this field. And then with this metric, we can talk about convergence. And so first thing we say, a sequence Zn converges to, say, W if and only if every epsilon bigger than 0, there exists a delta bigger than 0, such that Zn minus W is less than epsilon. Oh, I shouldn't say delta, it exists some capital N for all n bigger than capital N. So obviously capital N depends on our choice of epsilon. Yeah? So this comes to the picture. This is our W, and insisting that this is true is like insisting that all the Zn for n bigger than capital N are inside a ball of radius epsilon around W. So all of these guys are inside here. So Z capital N plus 1 is inside here, Z capital N plus 2 is inside here, and then so on, every single one of them from then on. Yep. So that is convergence of a sequence to some particular point in the complex numbers. Yeah? Cool. So this is completely analogous to convergence that you've learned already in real analysis, except now we have a different metric. We have this metric that defines distance between points on things that we represent as a plane. Okay, so as a consequence of this, if Zn goes to W in this sense, then the real part converges to the real part, and the imaginary part converges to the imaginary part. Which you can see from the picture, right? Because what is the real part? The real part is just, well, actually the real line is not over here, potentially. The real part, real line, can be whatever the real line is. Let's say the real line is over here. Then if we just project down these complex numbers, we'll have their real parts, right? So the real part of W is here, and the real part of all of these guys live here, yeah? And you can just see that if all of these guys, Zn plus 1, Z capital N plus 2, all of them inside this ball, then when we project them down, they're all inside this interval around the real part of W. You can just see it, yeah? Cool. And if we project onto the complex numbers, let's say they're over here, the same thing, right? If this here is the imaginary part of W, then if this is true, then the projection onto the imaginary part also have the same property. So it's immediately the case that the real part's converging to the real part, the imaginary part's converging to the imaginary part. Yeah? No surprise here. Cool. So here's a theorem. So recall what a Cauchy, you guys have all seen what a Cauchy sequence is, yeah? Maybe not everybody. So a sequence is Cauchy if for every epsilon bigger than 0, there exists capital N belong to natural numbers, which will depend on epsilon, such that I should call the sequence something, Zn, such that Zn minus Zm is less than epsilon for all Nm greater than or equal to capital N. That is a Cauchy sequence. Okay? So, here's a theorem on the real line that if you have a Cauchy sequence, then it actually tends to a limit. And that property is called being complete. Any space for which a Cauchy sequence has a limit is called a complete space. Yeah? And for most of the spaces you've learned in elementary math, that's kind of obvious. In higher math, this is a really important property that isn't obvious at all, but it's very, very important. It's very useful and significant theorem to actually have that this be true. So I guess some of you are doing real analysis, right? Or will do or have done real analysis. So when you do real analysis, you learn about Lebesgue measure, right? Which is a more general way to measure sets of the plane, which allows you to define something called the Lebesgue integral, as opposed to the Riemann integral, which you learned in calculus. And one of the main purposes of the Lebesgue integral was to be able to define this set of functions that were integrable in the Lebesgue sense, that their integral to some power was finite, and have that thing be a complete space. That's our so-called LP spaces. Whereas if you just do this with a Riemann integral, it's not true. So the space of Riemann integrable functions are not complete. So a Cauchy sequence in that space with the norm defined in terms of the difference of the integral of the function in the Riemann integral sense, that thing is not complete. So a Cauchy sequence doesn't necessarily have to have a limit inside that space, which was holding back analysis for a fair bit until this more general notion of integration, Lebesgue integration, was developed that allowed us to discuss a class of functions that were integrable and that were a complete space. That allowed us to minimize over that space of functions, for example, and know that there'd be something coming out that was still integrable in the limit, allowed the beginning of calculus variations. So this completeness property kind of seems obvious to you, perhaps, but isn't obvious at all in higher math, and is quite important. However, it's true for the complex numbers, and it's rather easily true because it's true for the real numbers. So this is a very basic theorem. The complex numbers are complete. And it follows from the fact it's true for real numbers kind of easily because we have every complex number is the sum of a real plus an imaginary part. So if we have a Cauchy sequence in the complex numbers for the same argument as this, the real parts will form a Cauchy sequence and the imaginary parts will form a Cauchy sequence. And both of those things will have a limit inside the space of real numbers, right? So then that limit for the real parts and the imaginary parts will also be the limit for the sum of the real plus I times the imaginary part. So it's not a surprise that this is a complete space because real numbers are complete. And if we take two complex numbers, so I'm just going to write in the language of maths this observation over here. If we have two complex numbers, then the difference between them is going to bound above the difference between the imaginary parts and the difference between the real parts. Cool. So we don't have to worry about the limit of a Cauchy sequence falling outside the space. All right, let's start to define sets in the complex plane if we have time. We don't have much time, so a little bit of this. So sets in the complex plane. So in standard complex analysis books, they will call things a disk instead of a ball, just because of just historical reasons. However, I'm so used to writing balls that I will forget to write disk, so I'm just going to call it a ball right from the beginning. So we're going to define this thing, the ball around the complex number is the set, let's call it actually W. The ball around the complex number W is the set of all Z, obviously in the complex plane, such that the distance of Z away from W is less than R. Okay? So obviously we visualize this. That's my pen's die. So W. This is R. It's the set of all points whose distance away from W is less than R. Yeah. So in traditional complex analysis books, so often this is called, or this is written as dr of W, and it's exactly the same thing. They just write D instead of a B. Okay, so if you look at past midterms, which is something we're going to have to do a lot going forward, you will often see this instead of this, but it's exactly the same thing. Okay, so this is the disk. The closed disk is, so I'm going to write this. It's almost the same thing, except now it's the closed disk, so the inequality is not less than, it's less than and equal to. Okay, so I draw the picture, it looks kind of the same, but now we're including the outside, you know, the actual circle that defines this ball, not just the inside of it. And given a subset of a complex plane, which is just, you know, a set of points inside this complex plane, so given omega contained within the complex plane, we say Z, let's get rid of this, is an interior point if, so I'm going to write this notation if and only if, that means we're doing a definition. So Z is an interior point if and only if B R of Z is contained within this set for some small r. Okay. So, for example, the set of interior points of the closed disk, right, is the set of points where we can fit some little disk inside that point and still be inside the set. Yeah. So, what points will that be? Well, that'll be any point whose distance away from W is strictly less than R, right? Because if the distance away from W is strictly less than R, we can fit some tiny radius around that point and still have it inside the ball. Yeah? Yeah? Whereas if we are actually on the boundary, which we'll define more rigorously later, but if we're on the outermost point here, on the circle that defines this ball, yeah, then that thing can't be an interior point because I can't fit a ball around it and still be inside the closed ball. Yeah? So if I take the closed ball, the set of interior points is the set of points whose distance is strictly less than R, in other words, the actual ball itself. Yeah? So mostly, this is the more natural object. We'll be dealing with this, sometimes with the closed ball, but the interior set of points, the set of interior points of the closed ball is just the open ball. Cool. All right, so that will be it for today.